Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 38. In this lecture, we'll discuss Bernoulli's equation. This topic is covered in Chapter 14 of our textbook by Surway and Jouet. In our last lecture on fluid dynamics, we discussed the flow rate of a fluid in a conduit. In this context, when I say a fluid, I mean a liquid or a gas, and when I say a conduit, I basically mean a pipe or a hose, or for example, air ducts in an air conditioning or ventilation system. In our last lecture, we learned that the flow rate is equal to the cross-sectional area of the pipe times the fluid speed. Recall that the flow rate essentially tells us how much fluid is passing through the pipe. A little more precisely, the flow rate tells us the volume of fluid, usually in cubic meters, that is passing through the pipe per unit of time, usually per second. Now, discussions of flow rate are relatively simple so long as the pipe is uniform in cross-section. Realistic pipes, however, often change their cross-section. In other words, they can get narrower or wider. We like to know what happens to the fluid when it passes through a segment of the pipe where the cross-section changes. Remember that we always assume that the pipe is filled to capacity and that the flow rate on the left of any segment of the pipe is equal to the flow rate on the right of that segment. What this essentially means is that whatever enters the pipe must exit the pipe. If 100 liters per second enter the pipe on the left, then 100 liters per second must exit the pipe on the right. This essentially means that the fluid is not getting backed up and that the pipe is not clogged. In our last lecture, we found that these assumptions lead to the continuity equation. The continuity equation tells us that the cross-sectional area of the pipe times the speed of the fluid on the left end is equal to the cross-sectional area times the fluid speed on the right end. In this particular example, if the pipe is getting narrower, then A2 must be less than A1. In that case, the fluid must speed up. In other words, V2 must be greater than V1. Now, it turns out the profile of a pipe can change in other ways as well. For example, the elevation of a pipe could change too. This is, for example, what happens when the pipes in the plumbing in your home change from the first floor to the second floor. When a pipe carries water from the first floor of a house to the second floor of the house, its cross-sectional area might remain constant, but its elevation or height relative to the ground could change. Of course, you could have a combination of these two effects. You could have a situation where the cross-sectional area is changing and at the same time the elevation of the pipe is changing. We already know that when the cross-section changes, the speed of the fluid changes. That's a consequence of the continuity equation. The question now is, what effect does a change in elevation have on the properties of the fluid? The answer to that question is provided by the Bernoulli equation, which is the main subject of today's lecture. Bernoulli's equation tells us what happens to a fluid as it passes through a pipe segment that changes both in cross-sectional area and elevation. To better understand Bernoulli's equation, we're going to derive that equation here. So consider a pipe segment and imagine that the fluid is flowing from left to right inside this pipe segment. Note that both the elevation and the cross-sectional area of the pipe segment can change. To have a concrete example in mind, you could imagine that this pipe segment is really just a section of the water plumbing in your home. So you can imagine that water is being carried through this pipe segment from, let's say, the first floor to the second floor of the home. To derive Bernoulli's equation, we need to understand what happens to the energy of the fluid as it passes through this pipe segment. And to understand the energy, we need to calculate the work that is done on this fluid by pressure. Now note that the fluid shown here is really just a section of a much more extensive fluid system. So you have to imagine that there is fluid on the left of this pipe segment as well, and that fluid has its own pressure. That pressure exerts a certain amount of force on the fluid in this pipe segment. Let's call that force F1. So you have to imagine that all the water molecules to the left of the pipe segment are exerting a certain force, F1, on this fluid element. As a result of this force, the fluid element will move to the right by some distance, delta x1. In doing so, that force is performing work on the fluid. We want to calculate that work. The work that's done on the left of the pipe, we'll call that W1, and W1 is simply equal to force times distance. A little more precisely, recall from your course on mechanics that for a constant force, work can be expressed as force times distance times cosine of the angle between the force vector and the displacement vector. In this particular case, the force points to the right and the displacement of the fluid element is also to the right, so the angle between those two vectors is simply 0. So we can express W1 as F1 delta x1. Also recall that pressure is defined as force divided by area. By rearranging that equation, we can express F1 as P1 times A1. Now here we're talking about A1, which is the cross-sectional area of the left end of the pipe segment, and delta x is the displacement of the fluid element. So when we talk about A1 delta x1, we're really talking about the volume of this region here. This is really the volume of fluid that is entering the pipe segment. So we'll express A1 delta x1 simply as V1. Now there is also fluid to the right of our pipe segment, and that fluid can also exert a force on the fluid inside this pipe segment of interest. Let's call that force F2. So all the water molecules on the right are exerting a certain force on the water molecules inside this fluid segment. We're calling that F2. We want to calculate the work that's done on the right end of the pipe segment, and we can do the calculation in a very similar manner. The work that's done on the right end, we'll call that W2. That's going to be equal to F2 times delta x2 times cosine of 180 degrees, which is going to give us -1. Note that on the right end, the fluid is moving from left to right, so the displacement vector points to the right, but the force vector points to the left. The angle between those two vectors is 180 degrees. This is essentially a consequence of the fact that we're assuming the flow is from left to right in this pipe segment. So the work that's being done on the right end of the pipe segment is negative work. As before, we can express force as pressure times area, and then area times this distance here essentially gives us the volume of fluid that is leaving the pipe. So we'll call the volume of this region here simply as V2. Now we're really interested in the total work that pressure is doing on the fluid in this pipe segment. To find the total work done by pressure, we simply add these two results, and we find that the net or total work done by pressure is equal to the negative of delta P times V. And by delta P, I mean the change in the pressure of the fluid between the left end and the right end of the pipe segment. We're now ready to complete our derivation of Bernoulli's equation. Recall from your course on mechanics the conservation of energy equation. Conservation of energy can be expressed in many different forms, but this form is probably one of the more useful ones. According to this equation, the change in the kinetic energy of the system plus the change in the potential energy of the system is equal to the work that's done on the system by non-conservative forces such as friction or resistive forces. If friction or resistive forces or generally non-conservative forces are absent, then we can simply say delta K plus delta U is equal to 0. In the case we're considering, the only non-conservative force is the force of pressure. So delta K simply becomes K2 minus K1. That's the change in the kinetic energy of the fluid as it goes from one end to the other end of the pipe segment. Delta U is the change in the potential energy. Remember that the elevation of the pipe could change, and therefore the gravitational potential energy of the water molecules or the fluid particles can change. And the work done by non-conservative forces, we derived that on the previous slide. We found that the work done by pressure is minus delta P times V. We can rearrange this equation a little bit by bringing the work done by pressure to the other side. And then we can recall that kinetic energy is really 1/2 mv squared. So we'll write K2 as 1/2 mv2 squared, where V2 is the fluid speed on one end of the pipe and V1 is the fluid speed on the other end of the pipe. We also recall that gravitational potential energy is mgy. So we'll write that as mg delta y, and we'll leave the rest of this alone. We're almost done. We're going to now divide this entire equation by volume. We find mass divided by volume can be expressed as density of the fluid. Here also mass divided by volume can be expressed as density of the fluid. And of course, when we divide this entire equation by volume, this volume here simply cancels out. This final equation here is Bernoulli's equation. It's often written in a slightly more abbreviated form as follows. Bernoulli's equation says 1/2 times the density of the fluid times delta V squared plus density times gravitational acceleration times delta Y plus delta P is equal to 0. We'll have to do some practice problems to get comfortable with Bernoulli's equation, but note that Bernoulli's equation is really just an expression of conservation of energy applied to the fluid in a pipe whose cross-sectional area and elevation can change. Writing down Bernoulli's equation is relatively easy to do, but achieving a deeper appreciation for the significance of that equation takes a little more work. To achieve that deeper understanding, it helps to recognize that in Bernoulli's equation, pressure shows up side by side with kinetic energy and potential energy. This suggests that pressure can be interpreted as a type of energy. You can see that more clearly if you look at the SI unit of pressure. Recall that the SI unit of pressure is the Pascal, and that the Pascal can be expressed as a Newton per square meter. This, of course, comes from the original definition of pressure as force divided by area. Now we can manipulate this equation by multiplying the numerator and the denominator by a meter. This suggests that a Pascal is equal to 1 Newton meter per cubic meter. Now you may recall from your course on mechanics that a Newton meter is really a joule, which is a unit of energy. So we can say that a Pascal is equal to 1 joule per cubic meter, which is really a unit of energy density. So when we say that the gas inside a box has a pressure of, for example, 1 Pascal, we could mean one of two equivalent things. We could mean that the gas inside exerts a pressure of 1 Newton per square meter of area, or equivalently, we could mean that the gas inside the box has 1 joule of energy per cubic meter of volume. This in turn implies that Bernoulli's equation is really saying something very simple. Bernoulli's equation at its heart is really just saying that the fluid's energy density is conserved as it flows from one point to another. So Bernoulli's equation is really a balancing act between three types of energy. Bernoulli's equation is basically saying that as the fluid flows from one point to another, the change in kinetic energy, the change in the gravitational potential energy, and the change in the pressure energy must balance each other out. If the kinetic energy increases at one point, then the potential energy or the pressure or both must decrease. Let's do a practice problem now with Bernoulli's equation. The pipe shown here has a radius of 5 centimeters on the left and a radius of 2 centimeters on the right. Water enters the pipe with a speed of 3 meters per second and has a pressure of 200 kilopascals. What is the fluid's pressure at exit? So what we're looking at here is really a pipe segment that is part of a larger fluid system. Water is flowing from the left to the right. We can see that the liquid enters the pipe through a wide opening and exits through a narrow opening. Before doing any precise calculations, let's think about this conceptually for a minute. We know that according to the continuity equation, the speed of the fluid must increase. That's because we're assuming that the pipe is filled to capacity and that the flow rate on the left must equal the flow rate on the right. In other words, if we have 100 liters per second entering on the left, then we must have 100 liters per second exiting on the right. Also remember that we assume that the fluids are incompressible, which means the density cannot change. So if you're going to push 100 liters per second through a narrower portion of the pipe, those water molecules need to move faster. What this means is that the kinetic energy of the water as it moves from left to right must increase. According to Bernoulli's equation, the energy density of the fluid must remain constant. If the kinetic energy is increasing, some other form of energy must decrease. We can see that on average, the water molecules remain at the same height, so the gravitational potential energy cannot be changing. Therefore, it must be the pressure that's changing. If the kinetic energy is increasing from left to right, then the pressure must decrease. So we anticipate that the pressure on the right end of the pipe is less than 200 kilopascals. Let's now do the precise calculations and verify that guess. We'll start with the continuity equation, which tells us that A times V on the left end must equal to A times V on the right end. Remember that A is the cross-sectional area of the pipe. Here we have basically a pipe with a circular cross-section. So we're really interested in this area here. We can call that A1, and we can calculate A1 as pi R1 squared. Note that R1 is given to you as 5 centimeters. Convert that to meters, plug into that equation, and find A1. Do a similar calculation for A2. And then remember that V1 is given to us as 3 meters per second. Plugging all those numbers into the continuity equation, we find that the fluid speed on the right end of the pipe is approximately 18.75 meters per second. So as we suspected, the fluid speeds up considerably as it passes through the narrow portion of the pipe. We can now use Bernoulli's equation. According to Bernoulli's equation, 1/2 times the fluid density, here we're talking about water, times the change in V squared, so the final V minus the initial V. We've calculated the final V, or V at point 2, to be 18.75. Don't forget to square it, minus 3 squared, plus the density times gravitational acceleration, times the change in height. In this case, on average, the height of the fluid does not change. I'm essentially considering this middle line to be the average height of the fluid as it passes through the pipe, plus the change in pressure. P2 is unknown, that's what we want to calculate. The initial pressure on the left end of the pipe is given to us as 200 kilopascals. We can now plug in some numbers. You may have to look up the density of water. The density of water turns out to be 1,000 kilograms per cubic meter. This is an important number that you should probably memorize, And of course, G on planet Earth is 9.8 meters per second squared. You can now solve for pressure, and you find that pressure in this case is equal to 28.719 times 10 to the third pascals. So roughly 28 kilopascals. As we suspected, the pressure on the right end of the pipe is considerably lower. The previous practice problem may have seemed a little puzzling to you, as our calculations showed the speed of the fluid was increasing, but its pressure was decreasing. This seems a little counterintuitive, so let's try to understand it a little bit better. In general, the velocity of a single particle of the fluid has two components of motion. It has a drift component and a thermal component. What this means is that the instantaneous velocity of a molecule or atom in the fluid can be written as a sum of two different types of velocity. To understand these different types of velocity, let's consider what happens to this single particle as it passes through a pipe. In general, we assume that the flow is from left to right. So naively, you might think that this water molecule, let's say, simply follows a perfectly straight line from left end of the pipe to the right end of the pipe. In reality, however, if you could somehow zoom in on a single water molecule and track its motion, you would find that that motion is not really a very simple motion at all. In fact, it's quite a chaotic, random walk, sometimes upwards, sometimes downwards, sometimes even backwards, but on average moving to the right. So we can say that this water molecule is moving to the right, but at any given instant, its velocity vector may not point directly to the right. Like at this moment here, the velocity vector of the particle might point diagonally in this direction as shown. We can take this velocity and break it down or decompose it into two components: the drift component and the thermal component. The drift component is basically along the flow of the fluid. The thermal component is basically a random component. All of the molecules in the fluid essentially have the same drift velocity, but the thermal velocities are going to be different for every molecule at different times. This decomposition here is a little bit like decomposing a velocity into an x component and a y component. It's not exactly the same because the drift velocity might actually be in a different direction depending on exactly how the pipe is oriented. And the thermal velocity doesn't necessarily have to be perpendicular to the drift velocity. It could even be parallel to the drift velocity. The point is that every molecule has essentially the same drift velocity and a slightly different thermal velocity. This allows us to write the velocity of any one particle as a sum of two different velocities. We can say that the drift velocity points in the direction of the flow, and it represents the macroscopic or the large scale or the average motion of all the particles. At the same time, the thermal velocity is random. It reflects the microscopic or the small scale or the individual motion of the particles. By separating the velocity of the particles in this manner, we can basically separate their kinetic energies into a drift component and a thermal component. What we have been describing as the kinetic energy of the fluid is really the result of the drift velocity or the average velocity of the molecules. So as the molecules overall move from the left end of the pipe to the right end of the pipe, that motion gives us the kinetic energy of the fluid. The pressure, on the other hand, is the result of the thermal velocity or the random velocity of the molecules. We can think of pressure as a type of random kinetic energy. So pressure really is a type of energy due to motion, but not the drift velocity or the drift motion, rather the random or thermal motion of the molecules. We've already talked about this, of course. We've mentioned how a Pascal can be expressed as joules per cubic meter, and we now have better justification for thinking of pressure as a type of energy density. In the practice problem that we did, we saw how the velocity increases from left to right, but the pressure decreases. So what was really happening inside this pipe was that we started with molecules that had large thermal velocities but small drift velocities. So most of their motion was essentially in a direction perpendicular to the drift. But as they entered the narrow portion of the pipe, their thermal velocity became smaller, they lost pressure, and their kinetic energy increased because the drift velocity became larger. So the total energy of motion was being conserved. It was simply going from thermal velocity into drift velocity. Let's end this lecture with one last practice problem. Water enters a home through a pipe on the first floor and continues to the second floor as shown here. The pipe radius is uniform at 1 centimeter. Pressure on the first floor is 300 kilopascals. Calculate the pressure on the second floor. So what we have here again is a pipe segment. Water is entering the home. We'll call that y equals 0. And then the pipe has to move to the second floor at y equals 3 meters. Notice that the cross-sectional area of the pipe remains uniform. The radius is given to us as 1 centimeter. The velocity of the fluid is not given to us. It turns out we don't really need the fluid velocity in this problem. What we know is that the radius remains the same on the first floor and the second floor, and therefore the area must remain the same. If the area of the pipe does not change, then the velocity of the fluid does not change either. So the speed of the water molecules on the first floor and the second floor will remain the same according to the continuity equation. This already tells us that the kinetic energy of the fluid remains the same as it passes through this pipe. Of course, the potential energy will not remain the same. As you can see, the potential energy will increase, and this suggests that the pressure must decrease on the second floor. Let's do the calculations and find out. We'll start with the Bernoulli equation and plug in numbers. The density here is the density of water. We don't know what the speed of the fluid is, but we know that the speed does not change, so delta V squared should give us 0. The change in height is 3 meters, so we're assuming that the first floor is at y equals 0 and the second floor is at y equals 3. And then the change in pressure, of course, is simply P2 minus 300 pascals. We can now plug in some numbers. The density of water is 1,000 kilograms per cubic meter. G, of course, is 9.8. Plugging those numbers in, we see that the pressure on the second floor is indeed lower as we anticipated. Water enters the home with a pressure of 300 kilopascals, but by the time it reaches the second floor, it will have a pressure of approximately 270 kilopascals. And that is the end of this lecture. Thank you for your attention.